Okay. I guess I'll just start. This is kind of a follow-up. It's very connected to the previous one, right? Which I just told you guys. So this might be a lot of this is going to be review because I think it's like we're basically covering the exact same thing we did last time, but now we're saying, okay, how do we actually make code for this thing? So yeah. Again, to start, we have workshop coming up very soon. So hopefully you guys have found data set. If you guys haven't, do that as quickly as possible. Okay, I forgot to update this. This meeting is in 2:15. Next meeting is not going to be in 2:15. In fact, maybe I should edit that right now. Next meeting in whatever, 515, right? It's the normal location, I think. So next meeting is going to be in the normal location. It's just this week. Just this week we have it in this room because our room was booked. We only have a couple workshops left. I think it actually might be, I forgot to update the slide. I think it might actually even only be 2 workshops because we don't have a workshop the week of Thanksgiving break, right? So I think that's something like, it's like what, week 5 or 6. So we don't meet on finals week. So that's like 4 weeks. We don't make Thanksgiving break. So that's like 3 weeks. I think the submission is last week. So yeah, it might be 2 workshops. I mean, you can check. The date is Friday, November 29th. So just check on your phone, I guess. And now neural network in Pytorch, that's kind of what we've been building out to, right? You guys kind of now understand, hopefully, at least in general, you have some data. You want the neural network to learn from the data. You kind of know last time we went over the structure of the neural network, which I'm going to go over again today because I think it's really important. Now we're actually going to write the code for it. And I'm going to give you a general outline for the code with a couple key things that you need to have. So review of perceptrons. I'm not going to go over this too much, but if you have any questions, let me know. It's kind of space for me just to review it, and then you guys ask questions about it. But right, each perceptron takes in some input. So let's say the input was 4, -1, and 2, and it has a set of weights. Weights are basically just what it multiplies each input by. So let's say, if in this case, let's say the weights, I'm going to call it W. I'm going to call it W1. W2 and W3. Let's say the weights are 1, 2, -3. Then it takes 4, multiplies it by 1, you get 4. Hey, what's up? Yeah, so I'm kind of doing a review of how neural networks work and then how we're going to program them. So again, each perceptron multiplies each input. 4 times the first weight, you get 4. 2 times the second weight, you get -2. And -3 times the third weight, you get what, -6, right? So each of these lines basically represents that you're multiplying it by a weight. And then this circle represents that you're going to add them all together, right? And that output is sent out. It's going to be sent out through an activation function. Most of the time we talked about the ReLU activation last time. So in terms of the activation function, the ReLU activation is super simple. If the input is negative, it outputs 0. If the input is positive, it keeps it the same. So in this case, my input was 4, -2, -6. So that's basically what, -4. So -4 is the output here, but really after the ReLU is going to output 0. Because it's a negative number, it will output 0. The other thing I actually didn't mention is that pretty often perceptrons actually are inputted with one more number. In addition to the weights, they have one number called the bias, which is called B. Bias is super simple. If we take the number 4, let's say, that just means we also add 4. So in this case, let's say our bias was 4, we would just add 4 to here, and this would actually become 0. So bias is just an extra number that you add in, and you don't multiply it by anything. It's just a flat kind of addition that you do. So yeah. And the reason we have this ReLU is because ReLU is nonlinear, and we want our output to be nonlinear because, in general, your problem, whatever you're trying to solve, is going to be nonlinear. Like we're trying to classify cats and dogs. That's not a super linear problem, right? They're complicated problem. We want it to be more complicated, so we just add something that makes it more complicated. You add the bias. Yeah, so you add the bias to the sum. So it's in here. You can kind of think about it like a fourth input that gets multiplied by 1. I don't know if that's helpful. Then you can think of B, and then it gets multiplied by 1, no matter what. And note that the B is also learned. So over time, it will change when you try to make it better. Yeah. And then now that we have these perceptrons, we can take a bunch of them. So each of these ones is going to be a perceptron, right? Then you have your inputs, right? So your inputs are going to be whatever model you have. I don't think you have the weather one, but sure think. Let's do the housing prices. Let's say you're trying to predict like real estate market. You're trying to predict a house price of a house given like the square feet of the house. You have, I don't know, square feet. If it's like the location, let's say, which I guess would be like two numbers, like X and Y. And then I don't know, you have like if it's like number of bedrooms, whatever, right? Stuff like that. So you have some house with like, in this case, let's say for an example, 2 bedrooms located. I'm gonna have like 2 inputs for the location. Located at 100, and then it's located at 20, and then square feet is, I don't know, 1,000 square feet. Right? You would take each of these inputs. If you had just one perceptron, you would take each of these inputs, multiply them, add in the bias, and then do the ReLU activation, right? Taking out negative numbers. That's kind of what we covered last time. So this perceptron, it operates on 4 inputs and has 1 output, right? Or it can output on any number of inputs. What we did after that was we kind of tried to stack a bunch of these because it's kind of too simple to just have one, right? Our problems are usually pretty complicated. So what if we had one here, and then we added another one here? And then now we have 2 outputs, and we can actually feed these 2 outputs into another perceptron. We do this. And what we have now is basically a much more complicated algorithm that can basically work on more complicated sets of data. And as you add more neurons, it obviously becomes more complicated. There's more multiplication, there's more additions. It can kind of understand more complicated data. And this is what's called the neural network. Because each of these circles, which are called a perceptron, they're also called neurons. And so together they're called a neural network, or sometimes they're called a multi-layer perceptron. Each of these layers is called a linear layer often. Linear because without the ReLU activation, it is just a linear function. And usually the ReLU is kind of added in between here. Like, let's say I do here, I do ReLU. So it's kind of something else. And I'll say also do it here. ReLU. And I'm just going to represent this block to say like, okay, you're going to take all the inputs that are less than 0 and set them to 0. And as I was showing on the slides, you can have multiple of these hidden layers, and now this make your model more complicated. And if you have a more complicated problem, you might need more layers. So there's kind of to think about now this how this works in code. You need to decide like a couple things, which is how many linear layers do you want in between? How many hidden layers do you want? How many inputs and outputs do you have, right? Theoretically, if I wanted to, I could have, let's say here I could have 2 outputs. Let's say I'm predicting 2 numbers about this house. Instead of just predicting the price of the house, I'm also predicting, I don't know, some other quality. I can't think of one right now. Or if you're doing a classification problem where you're picking, if it's let's say you're picking, what do we have? We had an example about like books. What is a book a romance novel? Is it a nonfiction novel? Like what type of book it is? What genre? Then you would have a 1 neuron for each class. Those are called classes, like cat and dog are class, romance, nonfiction, sci-fi, whatever, thriller. Those are each a class. So you'd say, okay, how many classes do I have? Let's say I have 3 classes. You have 3 outputs, and each one would just represent the confidence of the neural network that it's that output. So let's say, I don't know, you had your first one is romance, your second one is sci-fi, last one is fantasy. And obviously your inputs here would then be completely different, right? Your inputs might be, I don't know, whatever, author. Although I'm not really sure how you'd input the author as a number, but the author, I don't know, pages, or the plot summary might be kind of important, but I don't know, you have to decide how you put plot summary as a number. It's kind of difficult. But yeah, let's say you input a different set of numbers and you'd have to train it completely differently, obviously. But then the outputs here would be 3 outputs, and it would output its confidence that it might be one of these. So let's say, in this case, it's very confident it's a romance novel. You might output something like 0.8. Then it might output like 0.1 for sci-fi, and maybe it thinks that it's like 0.15 for fantasy. And you'll notice these don't have to add up to 1. It's not actually a probability because the neural network kind of isn't smart enough to actually make a probability. It was also like technically not a goal of this to add up to 1. And there's something you can do to actually make this into a probability and kind of rescale it, but we'll talk about that later. Or actually, I'll just tell you now. If you want to turn these numbers so that they're actually into probabilities, there's something called softmax. And this will basically just take a set of numbers and it will kind of rescale them so that they actually like add up to 1 and represent a probability, which will be useful if you're trying to like interpret the neural network. So if you ever see that online that people are adding a softmax for their classification, that's it. The next thing you want to choose is again your activation functions. So when I talked about each of these neurons is just doing multiplication and addition. So that means that those are all linear like kind of operations. And if you know about linear operations, then basically like multiplication and addition, they're all distributive, commutative. Those properties, they apply to linear operations. And it basically means that when you do like a multiplication here and a multiplication here, you can just represent that as one multiplication, right? If you didn't have this ReLU, let's imagine we didn't have ReLU. If we didn't have ReLU, then we just multiply here and we just multiply here again. You can represent that as one multiplication because you just distributed it, right? And so what that means is if we build a super complicated neural network like this one, or like the one I had on the slides previously, it actually would just become 1. It would just kind of distribute back into 1. So we just add something that's non-linear in between, which I talked about last time. And this basically means that you can't distribute over a non-linear operation. So that means it doesn't collapse into like one thing. And this can be basically anything that's non-linear. But generally, we try to do something super simple. And in this case, what's super simple is what's called ReLU. It seems like it's complicated, but again, it's just if the number is negative, it becomes 0. If it's positive, it just stays the same. And that is technically non-linear, right? It's not a straight line. It's like curved right there. Or I guess it's more like broken. So we just add that in between. And so now again, we take our inputs, multiply them, take out negative ones, or turn them to 0. Do that again, add them together, multiply them, turn the negative ones to 0, output them. And theoretically, you would repeat that process for however many layers you have here. I believe that's, yeah. So that's like a super sped through review of a neural network. It's kind of important to review what are the decisions you're making when you're actually programming this, because a lot of specific math I've talked about, like the multiplication or the ReLU, Pytorch will do for you automatically. So the decisions you actually have to make are how many hidden layers do I have in between my inputs and outputs? How like wide are these? So here there's 5 in each of these hidden layers. Pretty often these will be way wider. In fact, usually the structure tends to be you have a set of inputs, and I'm just gonna like literally represent the bar. So like let's imagine the bar is like how many inputs you have. Usually it gets wider either once or twice, and then it starts to kind of get narrower. And then let's say your outputs are here. So you'll have like, let's say 4, then you'll go to like 10, then you'll start going back down to 8 to 4 and so whatever. That's like kind of just a heuristic. Again, like we don't really understand how these work totally, so it's kind of a guess, but that's usually how it happens. You definitely don't want to like bottleneck it all into like one neuron in a layer. Usually you want your layers to like not change too dramatically. Stuff like that. It just allows data to flow through. Are there any questions? Because, yeah.
So determining the width and how many layers is basically trial and error, right? To get the best result?
Yeah, pretty much.
Okay.
Yeah. Yeah. I mean, it's because it's, yeah. Like you can think of like, okay, a more complicated one, like you can think of how complicated your problem is. Like it's more complicated, you want more, if less complicated, you want less.
Yeah. Like,
yeah. I'll also talk about how you can decide, like let's say you run your model and you get certain results. How do you decide if you want to make it smaller or bigger? I'll talk about that in a second. Yeah. So hopefully that was mostly a review. I don't know what you guys like remembered and what you guys forgot. So like if there's something like specific that you want me to review this. Okay, I'm gonna move on then. Wait, I'm recording this, right? Better. Yeah. Okay, then again, reviewing, this is a lot of what you're going to be coding, which is the training and testing loop. So in terms of the output of this neural network, right, it depends entirely on the weights that's multiplying by, and also actually the bias, I guess, that's adding. So it depends entirely on just these numbers, right? So if you change these numbers, the output will be completely different because it's going to do a different computation. Actually, by the way, I'm going to say this is important to remember. Parameters. These numbers that it's multiplying inside, specifically the weights that it multiplies the inputs by, are called the parameters. And also the bias is also considered a parameter. So when your perceptron takes in an input like 2 and it multiplies it by 5 to get the output, 5 in that case is the weight. And if you change 5 to a different number, if you change the weight, your output will be completely different, right? So that's just kind of the intuition. You start off with random weights and you're trying to adjust them such that they actually make a meaningful output that's correct. So our problem is basically how do we adjust these parameters into the right values that give us the right answer. And the way we do that is we make small little adjustments based on the data. So again, we have a bunch of examples. We see how good it performs. At first, it will choose randomly. We'll see how good those results are. We'll score them with our loss. And then based on our loss, we can adjust what the parameters are. Yeah. And the other thing I talked about is also training and testing. So I think I can use that here. Yeah. And the very important thing in your code is you're going to have to select, you'll have to import your data, right, as tensors. And I talked about this in the data processing, so I'm going to review those slides if you remember that. But basically, you want to make sure that it's not just memorizing whatever data you're feeding into it. You want it to actually learn general rules. So for that, you have some sort of testing data that it can't learn, and you test the model on it. The same way your professor doesn't give you like the test before, and he wants to see how well you perform, like in quote unquote real life, without having to know the answer. And oh yeah, about the designing neural network with Python. So one thing is if your model is memorizing the data set, one way you can tell is you will want to use matplotlib. And matplotlib can basically help you to make graphs. And one graph you can make is basically the loss over epochs. And what's epoch? Epoch is just how many times you run the training stuff. So let's say you've run through a bunch of examples and you updated the weights. That's one epoch. You run a bunch of examples, you update the weights again. That's the second epoch. Run through examples, run through the weights. That's the third epoch. And you'll keep on doing that consistently. And when you start at first, your loss will be super high, right? Because again, your weights, they start off random. And so therefore, it's going to do a bunch of random multiplications, and it's going to just output a random result. And it's probably going to be really wrong because it's just guessing random. Then it makes a very slight adjustment, and it'll get better. Next epoch. Maybe it'll get better. Maybe it'll actually get worse once, then it'll get better. And basically what you'll see is you'll see that it kind of like tends to go down, right? Over time, hopefully, if you're honest. But this is when it's training. What you'll do at the same time is you'll probably have the testing, right? Which is basically testing, it doesn't actually learn from it. So you put in the inputs and you get an output, but you don't let it update the weights. You don't let it learn the testing data. Why? So it doesn't memorize it. Because if it learns from it, it can try to memorize that data, and then it's kind of the whole point of the testing data set is kind of not there. It's to see how it would perform on data that it hasn't learned from. So what you could do is at the same time, you could plot what is the loss of this, right? This is the blue line. What is the loss on the testing data set? And what you might notice is it might be like a little bit higher, but you don't really need to worry about that. And that means it's good, right? Like it's doing pretty well on the training, and it's also doing pretty well on the testing. But what you might have sometimes is that it suddenly goes to very low, like almost 0 on the training. And meanwhile, on the testing, it goes up. What does this mean? Well, this means that for every training example, it gets it perfectly right, which is kind of unrealistic, right? It shouldn't perfectly know every example. The only way it can actually do that is if it's memorized every example. And you'll notice that if you're doing worse on the real world kind of like data that it hasn't seen before, on the evaluation on the test, it does worse. So that's how you know your model is overfitting. And basically, it's quote unquote memorize the data set. Kind of if you think about it intuitively, how is it possible that you can memorize something? There's two ways. It's easier to memorize something if there's less things to memorize, right? So if it's memorize the data set, that probably means your data set is too small, right? If your data set if you think your data set is a good size and this is still happening, then maybe your neural network is just too huge. It's so huge, it's like, you can memorize it all just because it has so many weights and so many biases. It can kind of be able to just memorize it rather than, rather than actually learn generalization. So you need to make it kind of stupider. So if you see this happening, then that's one decision that could make you decide to make your neural network have less layers. And usually you would cut off a whole layer rather than making it wider or narrower, you would cut off a layer. But that kind of depends. You can test that kind of stuff. So yeah, that's a review of training and testing and kind of getting the loss. Last thing is optimizer. Like I said, the optimizer basically sees what our loss is, and based on that, it will update our parameters to output a very slightly better number, a very slightly better result. So instead of being 99% wrong, it's 98% wrong, and then slowly every time it gets slightly better, and over time it gets much better. And what's called the hyperparameter for that is the learning rate. So one thing I do want to clarify here is we have our parameters, right? And these are the parameters inside the model that we're multiplying our weights by, that we're adding stuff to. But we also have our hyperparameters. And the reason they're called hyperparameters is sounds sort of like a really cool name, but really just more parameters that decide how these parameters are listed, right? Because these parameters are constantly changing and we don't decide them. The computer is deciding these. Hyperparameters are ones that we're actually going to decide. So for example, technically you could say that the width of this neural network is a hyperparameter, right? Because these parameters are basically, they kind of depend on the thing, you don't decide them, but how wide we make it is a hyperparameter, right? So you could say just literally neural network size. I mean, depending on who you ask, that could become some hyperparameter. Another one is the learning rate. Or often you'll see it called just LR. So again, this is a number that you decide at the beginning. And basically decides how much are your weights going to be updated each step. And each time it sees how wrong it is, it makes this optimizer step, and it updates each of these weights inside by a little bit to get a slightly better result, right? And the learning rate adjusts how small is that tiny step that it makes. Now, usually on our examples, we only want to update it a tiny, tiny amount, right? Because we want to learn a kind of slow amount, because if you kind of make huge jumps, you might make optimizations that are wrong because you're only updating based on some examples, right? I kind of covered this more last time, but basically you want to make small steps to kind of learn very slowly. So your learning rate is going to be somewhere in the range of 0.01 to 0.0001 or something, maybe. I mean, this is a very small learning rate, but probably with 2 zeros or something like that. Yeah.
Can you decrease the learning rate for future epochs?
Okay, actually, yeah, that is in Pytorch. Yeah, there is what's called learning rate decay. So if you imagine when you're first learning, you might want to make big steps and big changes because at the start it's random. And then as time goes on, you actually make smaller steps because you're kind of getting closer and closer to the solution. So there is something called adjustable learning rate. And that's implementable in Pytorch, where your learning actually changes over time. And you just say, okay, take my learning rate and here's how I want it to change. In that case, you're still actually specifying it because you're just saying, I want my learning rate to be like this. Whatever. And these would still be pretty small numbers, like to be 0.01, this would be 0.0001. But I'd say in most cases, just start with just not learning rate decay, just start with just a static number. And then if you want, you can look at how your learning rate decay. And yeah, the other hyperparameter, I guess, is what type of optimizer you want to use. And there are different kinds, but in Pytorch, I would strongly recommend you use Atom. That's kind of the standard optimizer that everyone uses because it kind of helps you find the bottom the fastest. without like kind of accidentally getting to like the wrong location. Talked about this more last time. If you guys remember where we're trying to find the right weight, right? So we have weights. And then let's say when our weight is like 4, we get this amount of loss. So this on the y-axis, we have loss. Right, we have this amount, maybe we have this loss. And basically what we're trying to do is we're trying to find like, really this would follow some sort of graph, right? And we're trying to find the weight with the lowest loss. So what Adam does is it kind of acts like a ball rolling down a hill and it tries to find the lowest point. And it tries to do that without getting stuck here. You see how there's sometimes like, they're called local minimum. And it doesn't want to get stuck here. It wants to get to the actual lowest one. Overview. Again, this is kind of where we left off last week. I'm just again going over a review of it because where basically the code is basically going to be pretty similar to this. We want to initialize our data when I talked about training and testing data, right? Testing data is like usually 30% of your data you're going to split that the model can't see that's going to be tested on. You're going to decide how many layers you want. You're going to decide how deep each layer is. You're going to decide what activation you want to use. So it can be any nonlinear function, but most of the time you use ReLU. Optimizer is like actually always Adam. Activation, maybe sometimes you want to change it, but optimizer, honestly, I've never changed it. Loss, again, this is how you calculate your loss, how bad your result is. So most of the time you use mean squared error. If you remember I covered last time, mean squared error. It's not as complicated as it sounds. It takes the average, the mean of the square of the error, and error is just taking the difference. So if the output was supposed to be 5 and it said 1, then it would take that error. You take 5 minus 1, so the error was 4. You would square it, and then you do that over every example, and you calculate the average or the mean. So mean squared error. The other one is if you're doing a classification problem, right? Like your output is romance, sci-fi, fantasy here. Like you can't really take a difference between, let's say the actual answer was sci-fi here. You can't really take a difference between romance and sci-fi, right? It's kind of strange. So silly for that, you use a different loss function called cross entropy loss. And these are both implemented in Pytorch. And then I talked about the training loop. That's on the slides right there, right? You want to make a prediction. You want to calculate the loss. You want to update the model based on that. And then in your testing loop, you want to make a prediction. You want to calculate the loss. Does that all make sense? I'll make sure it does because basically we're going to be writing the code. So hopefully you understand what the code is doing. Right. So in PyTorch, you're simply going to be making a class for your neural network, or I work on making a class. There's technically something you can do called making like a sequential, which kind of is like less code, but it's kind of hard to understand what it's doing because it kind of does this stuff automatically for you. You don't realize it's also hard to debug. So just for a moment, who knows what a class like in Python is? Kind of? No? Yeah? I don't know. If you got it, hopefully. I might review it real quickly, but you just say class, cat, whatever. And then you can define different functions under the class, right? Def, meow. And then it will say like, I don't know, print meow. Right? And then what the main class allows me to do is I can do cat equals cat, and then I could do cat.meow. Right? And then doing cat.meow will call this function as an transfer class. So in the same way, and now instead of making a cat, we're going to make a neural network, right? So PyTorch will do a lot of stuff automatically for you. So make sure the first line of code should probably be something like import PyTorch, which I'm sure you guys can figure out how to do that. Next thing you want to make is make your class, right? Like I said, but now you're going to make it whatever your neural network is. You call it NN, call it my model, whatever. And you're just going to want to put this inside the parentheses, which is NN dot launch. And you're going to want this nn.module, you can import it from Pytorch. And what this does is it basically does a bunch of automatic stuff in the background for you to make your class automatically do stuff like initialize these weights, update them based on your optimizer, a bunch of convenient stuff so that you don't have to do that math, yourself. And also it does it all like in an optimized way. So if you run on GPU, for example, it can run super quickly. And so for this class, there are two functions you want to define. So def your underscore init. Sorry, underscore is too much. And then your code here, right? Does anyone know what the init function does for a Python like class?
Constructor.
Yeah, constructor. Yeah, it's init. It's short for initialize. So it basically just means that when you make this is the first code is going to run. So this is going to start up. So when we start up, what do we want to do? Well, we want to basically tell it like, okay, a bunch of stuff about the neural network. And these are all your hyperparameters, basically. These are saying, okay, well, actually not all of them, but basically stuff, hyperparameters about the model itself. So like, how many layers do I have? How wide is each layer? What are my inputs and outputs? Right? Stuff like that. And usually here, you're literally just going to define your layer. So let's say I do self.layer1 equals, in this case, I want to make, let's say I want to make these layers, right? Which are the linear layers, right? In that case, you also, again, nn, I think it's like, you can import from Torch, you can import nn, and this will give you nn.module. It'll also give you nn.linear. And that will make the first layer. And you can keep doing that for whatever layers you have. You can also say like self.activation or whatever equals, and then actually it might be, ooh, my battery's running low. Eric, can you help me? Are you asleep? Okay, he's asleep. You can also say your activation function. I actually forget if it's from nn, but you can figure out where it's imported from. But in Pytorch, is it charging? In Pytorch, it's also just called relu. Crap, I haven't read the chat. Yeah, initialize is right. Yeah, and again, you want to decide more hidden layers. Because about hidden layers, generally, more hidden layers does make your model like more complicated. So it can do more complicated stuff. That's right. It might get a higher accuracy on more complicated problems, but you want to make sure it's not gonna like overfit. It's not gonna memorize the data. Anyway, so you might choose whatever relu, and I think in Pytorch it's just called relu, R-E, and then capital lowercase e, but capital L-U. And it's really just fine with that. I don't want to give you this exactly because like you can find this all online. But linear, you want to tell it how many inputs and outputs it has, right? Because like for example, here, let's say I had like 4 inputs. So that means for layer 1, which is right here, this layer, I'm going to have 4 inputs, right? And then how many outputs does this layer have? Right here in this example. Does anyone have any guess? 3. Yeah, 3. So it has these 4 inputs and it has these 3 outputs. So you would literally tell it, okay, there's 3 inputs and there's 4 outputs. All right. And if I had a second layer, then the same thing, I would say, okay, now there's whatever number of inputs and whatever number of outputs, and you can draw it out if it's helpful for you. So yeah, you basically just say, okay, here are all the layers I have. Here's how many inputs, here's how many outputs. And it will, yeah. And that way you're kind of deciding what's the depth of mine. So if I wanted a second layer, I would just say self.layer 2. Does that make sense? Yeah. And the reason you say self.layer 1 is basically, I mean, it's kind of like what object-oriented programming is with. So that could take a while to explain, but basically it just saves it with this self parameter so that later, let's say I define a different function. I'm going to call this function forward. Actually, sorry. Basically, you don't have to pass in self. Self will be passed in automatically, and it will be saved with it. Because you see this layer one, you defined it up here. So how do you access it in a different function? The way you do it is you just say self dot layer one. And this self basically lets it like kind of lets you use it in different functions. I don't know if you have questions about like self, like object-oriented programming, you can kind of there's a lot of resources online for it, or you can ask me. So next, that's kind of the initialization. You said, okay, here are the amount of layers, and yeah, here are the amount of layers. That's basically what you said. And here are the activations. You've also loaded activation. Now you write the forward function. So the forward function is the forward step, which means it's going this direction. It's taking in the inputs and it's returning the outputs, right? So to get an input, to get an output from an input, you basically take these inputs and you pass it through the first activation. Actually, wait, I'm just gonna. Actually, let's make our neural network like a little bit more complicated. Let's say that this is also a layer. Which actually makes sense because that's what we're doing here. So let's say I also have self the layer 2. So I've defined 2 layers. So to pass an input through, you literally just call layer 1. You'd say, I don't know, out 1 equals self.layer 1. So if this code kind of makes sense, you take self.layer 1 and you're putting the input into it, and that equals the result. So the output of the first layer is equal to the first layer, and you're putting in the input, right? So that should be basically representing you're putting in these inputs here, and it will give you a bunch of numbers out, right? So what happens after we pass it through the first layer to our inputs? Does anyone know? Especially on this diagram, you can see where it's going. Yeah. So here in this linear layer, it will multiply the weights in. Yeah. That's actually what we defined in layer 2. So we could pass through and say out 2 equals this, whatever, the output we got from the first input, and we do all the multiplication. Pytorch will do it automatically for you if you just do self layer 2 out 1. Right? So you take out 1 and then you pass it through the second layer. And that's basically doing all that multiplication and addition for you. So you don't have to do it all manually, right? There is something in between these 2 layers. Really, right? So let's not forget about that part, because if we just have linear and then linear, it's basically the same as doing one linear, right? Because linear functions, you can just distribute them and it becomes one function. So in between, we want to actually do the ReLU. So we could just say out 1 equals ReLU out 1, I guess. It just redefining itself. You can do this in Python. Where you say out 1 is ReLU of out 1. So now it's just redefining itself as the ReLU of out 1. And then you would keep doing this basically repeatedly, where you do self.layer1, your input, self.relu, or whatever, or you just write relu actually. Then you do self.layer2, then you do relu, self.layer3, relu, until eventually you have the output and you pass through all the layers and you just return it. So you just do return whatever you call your output. I don't know. Communicate. So again, in it, we define, okay, we have layer 1, layer 2, layer 3, layer 4, whatever. Then in forward, we just call layer 1, layer 2, layer 3, layer 4. And it's as simple as just putting the input into the parentheses inside each one. So if we want to, let's say, kind of make this more clear maybe with an example. If we have our input of like, here we had our input of 1,120 and 2, right? So in Python, that would be like a list 1,120 and 2, right? The path is through the first layer where it multiplies and adds them all together at each circle, right? Here it would multiply and add them all together, multiply and add them all together, multiply and add them. And it does that 4 times. Instead of having to do that manually, you just say, like, let's say in equals this. You say out equals, layer 1 in. So kind of as a concrete example of like what this would do. Obviously, you wouldn't do it with just one example. You would do it with like many examples, but because that's to learn from many examples. But this would give you the output from like one input. And when you repeat this with multiple layers, you get this kind of structure. Yeah. And so Pytorch will handle all the multiplication by these weights and biases automatically. You'll notice I never had to define the weights or the biases or anything. But you have to update them right now, because at first Pytorch will start them off random. So how do we decide what these weights and biases are? That was with, if you remember, our optimizer, right? And our loss. And so for that, we need to make our training loop. Oh, I actually had slides for this. Well, yeah, so this is a model. Now we need to initialize the loss, the optimizer, and the data. So data, I don't know, we talked about that previously in the data processing. So hopefully you guys can remember some of that. But basically you should have your data as like a tensor, which is kind of like you can go as a PyTorch, like an array of arrays or like multi-dimensional arrays. And yeah, so you have your data. You have to, here, MSC cross intermediate, this is actually how to do it, but I'll erase it for a sec. So you have train data, equals whatever. Test data equals whatever. And we talked about how you might load that in using pandas for CSV files or PIL for image files. And you can load it in and load in 70% into training and 30% into testing. The other thing is you want your loss. So you can literally just say loss, loss function. And this is how you'll calculate how bad your model is, right? And in our case, we can use MSC. Does anyone remember what that stands for? Yeah, mean squared error. So you take the difference between what the prediction and the actual was, you square it, and then you kind of the average over a bunch of examples. And this will basically just do that automatically for you. So you don't have to like do the difference in the squaring yourself. And then lastly, you have to say, okay, what's my optimizer? I'm going to say optimizer equals, and then I think it's like from PyTorch. Oh, you would import this from PyTorch. MSC is an import from PyTorch. I think from PyTorch, you can also import a library called optim. And you can do optim.atom. And then even actually before this, you might initialize your model itself. Yeah, we're going to put that there's only two outputs. Yeah, I should say model equals whatever class you define. So in this case, I call it my model. So I would literally call it my underscore model. Right? So there's no semicolons in Python. So what calling my model here would do is it would literally run this init function right here. And now all these layers are made, right? And now this model, we've defined also another function called forward. So you can use that function as well. And there's also a bunch of background stuff that Pytorch has done to make it like be able to be optimized and stuff. In fact, for example, one thing PyTorch implements automatically is if you ever want to look at your parameters, like what are actually the weights inside of these things, you can actually print, let's say, you can do model dot parameters. And PyTorch, because you did this line of code right here where it said nn.module, it will automatically tell you, oh, based on the fact that you have this amount of layers, these are the parameters you have. So model.parameters. But I mean, that's just kind of for informational reasons, or the Atom optimizer will actually, I think, take model.parameters as an input so that it knows what to optimize, I think. This is really bad handwriting. I'm having like trouble writing such lower down the board. My handwriting gets worse going down. So yeah, you've initialized, okay, here's my loss function, which PyTorch gives you. Here's my optimizer, which PyTorch gives you. Here's your model, which you've made. And here's the data, which we talked about in previous classes. Now we want to run through that data and we want to update our model. So that's the training loop. Here on the slides is kind of better. Honestly, explain whatever I'm going to draw. It basically you want a for loop. And the for loop is going to run, you know, let's say you have each loop iteration is called an epoch. So let's say you have 100 epochs. It's going to get a batch of training data. It's going to make a prediction. It's going to score that prediction with the loss function. So it's going to score that prediction with the loss function. And then it's going to update the model. And the way you update the model is with basically those 3 lines of code, which I don't know, I'm kind of running over time here. So I don't have much time to explain them. But basically, optimizer.0 grad basically resets the optimizer for like a new batch of data. Loss.backwards will do the backwards step, where based on the loss, it will update your weights. And then optimizer.step will actually like do that step of set updating the weights. Just like loss.backwards will calculate what it should update the weights to, and then optimizer.step will do that. One example you could do is, so let's say I want to take my model. I define here model equals my model, right? And I define a function called forward. And what this forward does is it returns a prediction, right? So when I say predict there in that for loop, I literally mean you do whatever model.forward. Let's say this is a training batch. So you call model.forward with the training batch. You would call the function that you've written. It would pass it through all the layers, and it will return an output, right? And the way you get the output is you say equals prediction equals the model dot whatever the model will output, right? That prediction. Then you calculate the loss. You say loss. People on the screen see this. You say the loss equals, again, whatever your loss is called. So I called it loss function here. You can go with something different. I call it loss function. And then again, your predicted. And then your actual. And then again, your actual, you would actually technically, I guess you'd say this train input. And this would be train output, I guess. Right, so like, let's say I had a bunch of data on, let's say the author, the pages, the plot summary, whatever, and whether it was a romance, a sci-fi, or whatever, I would split it so that whether it was a romance or a sci-fi was in the output here, And then all the inputs, which are like the number of pages and those numbers, stuff like that, will be on the inputs. And then you pass through, make a prediction, you compare it to the output in your loss function that you defined, you get a loss. And then lastly, you do those steps, which is optimizer.zeroGrad. So ZeroGrad basically zeros the gradients, which basically means it resets it because you're doing a new kind of training loop. It kind of needs to be reset every time. Loss.backward will kind of go backward through using this loss and see what are the updates I need to make. And then optimizer.step will step through and basically update each of your weights to be slightly better. And then when it makes it slightly better over time, 100 of times, then eventually you'll actually make a good model. Testing, I'm just going to go over this really quickly, but it's kind of very, very similar, where you also just call prediction equals model.forward, and you also calculate loss equals the loss function between the prediction and output, but you're not going to run those like optimizer.step parts, right? If you want for the testing also, oh, but no, okay, I guess the slides are, and it's meant to say no, but no training, no updating the model. If you want, you can also do with, what is it, torch.nograd. When you do this in the training loop, basically, it's kind of just a thing to make it run a little bit faster. It's not super important. But basically, if you remember, it will like calculate the loss and all that stuff. Torch is actually always constantly calculating in the background all this stuff to like figure out what the optimal number is. But again, you don't need to do that when you're just doing the test because you're not updating it anyway. So it's basically saying, oh, don't worry about the calculations for now. Just no gradient calculations. And the main thing is calculating the gradient, which like it's kind of expensive to calculate. So this kind of is recommended to do, and you'll see it often online. The reason I'm pointing it out is because often if you like look at online, you'll see people put this when they're testing, when they're running their tests. And the reason is just to tell the Pytorch, hey, don't run a bunch of like background calculations on this. We're not going to update our model based on this. Just literally just give me the output. I think that might be it. Yeah. Okay, sorry I went a little bit over time. If you guys have to go, that's totally fine. If you guys have questions, I'm here. I know I went through, I kind of started speeding through at the end, so that's my bad. But a lot of this is like the model is just literally just blank equals blank, right? Because all the math and like anything like that is all handled by Pytorch. It's really nice. Just remember you have your init function, your forward function, and then your training loop, which I kind of split it up across two things. Your training loop, which you start here, and then in your training loop, you to run this part repeatedly. Good. Oh, the one thing is a lot of you guys are using images, right? So if you're doing an image, you might want to use a convolution rather than just a linear layer. If you remember what a convolution does is it combines pixels that are nearby rather than kind of inputting all the pixels at once. So instead of doing linear, right here where you do self dot layer 1 equals nn dot linear, you say self dot layer 1 equals nn dot, this marker's dead. Self dot conv 2d, conv 2d. And yeah, and literally this would be the only line you would have to change necessarily. And you would have to specify the parameters for that. Is like, if you remember, the way it works is it takes an image, and let's say this image has a bunch of pixels. Or here, let's in this example, it only has like, was this like 5 pixels or whatever? But obviously, it would just work for bigger ones. Is it combines? Let's say here, it combines these two, then it passes over, and you remember it moves over one and it combines these four. Then it moves over and combines these four, moves over, combines these four. Then it kind of goes down, combines, and it like goes down like that, right? That's how a convolution works. So in this convolution, you just have to specify kernel size, and this little shape is the kernel. So in this case, it would be 2 by 2. Most of the time, the kernel size, I would say, is 3 by 3. And almost always it's square. So you can just give it one number and it'll assume square. So you can just say kernel, I think it's kernel size equals 3. Or you can just pass in the number 3, I think, and we'll know that it's a kernel size. So you can just pass in 3. And it will make a 3 by 3 kernel and pass it over, and it knows what that is. And then when you call layer 1, exactly the same will do number. And literally it will run the same in here forward. That's a really nice thing. The other thing is, if you remember, in between convolutions, pretty often you want to run a max pool, which does the same thing. Oh, I shouldn't really erase them. Okay. You have your image, and it also has like a little filter kind of thing that passes over. And instead of like doing the convolution where it like multiplies each one and adds them, basically like a perceptron for each kind of step, instead it will just take the maximum value. And so that's just called, I think, literally nn dot like max. Actually, forgot what it's called. I think I'm like 90% sure it's called max pool. And then the same thing here, where you have to specify what is the kernel size, which I would say 2, usually. And usually what people do actually for max pool is they don't have overlap. So if you remember, I passed it over, like I did one here and then I did another one here, right? With the convolution, right? And in this case, it actually takes 2 of the same values. For max pool, most of the time people don't do that. What they do is they have it, if it's 2, they have to jump over 2. And they just take it 2 at a time. And so for that, that's called the stride. Stride is how much it moves over. By default, it's 1. So you can just tell it to have a stride of 2. So, and you would still do really the same way. But that's basically it. Yeah, let me know if you have a question. Oh, never mind. Okay, I hate to keep you guys. I'm sorry. There's one more thing with convolutions, which is that you have the number of channels. You have in channels and out channels. This is basically, you're splitting your image into like really more than one image. If you have RGB images, you're not really dealing like this with one image. You really have 3 images, right? You have an RG, you have an R image, you have a B image, and you have a G image. And you basically pass that kernel over each one. And each one of these images is called a channel. So for your in channels, for your first convolution, it's always going to be 3 because you have R, G, and B. But what you can actually do is instead of passing the convolution over once and you get one image out, you pass a second convolution over and you get a second image. So you can actually increase the amount of out channels. So often you'll increase it to like 16 and then 32 or 64. And you'll basically increase the amount of out channels. This basically just means you have a bunch of filters running over and each filter will learn something different. If you want to talk to me about filters, they're pretty interesting actually, how the neural network can learn to actually detect like edges or shapes using these filters. Okay. But talk to me about that specifically because officially the meeting's over. And parents are
Also, you're not doing anything today. We're doing anything.
I got the basic. I got to the basic. Yesterday, there were no more glasses.
No. Oh, I heard like one was like that too.
Yeah, I want the call.
Yeah. What did you guys do? Oh, I remember that. Very, very.
Went downtown and then we like got It's only. We were
We were planning to go like on a house meeting today for Halloween, but we only in Santa Cruz. Unless it's like parties, but I'm going to go to like a. Yeah, I think it's
Yeah, we're here.
Yeah, it's images. Look at the library.
Yeah, sometimes random
And then just
random days.
Yeah.
UCSC, like
I mean, I tried to.
like some
My code is different, but I think it was this.
the employees at
I
the
think,
rec
I
center.
mean, it was.
Yeah, it'd be just someone there and then I've
Yeah,
never.
I did it
Is there any last
yesterday
questions on
during-
Zoom as well? Just type in the chat. I don't know.
That's actually crazy.
I was in English and I was like, I don't give a shit about
Finish
code.
that.
I did
You
it.
got one today.
What?
You got
It
confused?
doesn't-
Oh, hell no.
Yeah.
Yeah.
Yeah,
People first thing is CPU or so GPU, and I was like, okay.
Hello?
No, but
Gear.
Yeah, we can hear you.
Yeah.
Yeah, cool. Basically, I want to just have a better understanding about the flow of data going into neural net, just code wise. So like, basically, if I have like a
Yeah.
if I had a linear regression model, right?
Okay,
So,
yeah.
Alright, so basically, like picture wise, like how what you have on the board, you would have like such as you would have like the yeah. Okay, I don't know if you remember my problem.
Still works
Uh,
like that's crazy.
Yeah, for linear regression, I can draw it on the board, but actually, I would recommend maybe a different library than PyTorch. There's one called scikit-learn. Where's the caption? Is that why it's dry? Does it have a cap? Yeah, there's a library called scikit-learn. And if you Google scikit-learn linear regression, you're sure to figure it out. Here, I can type in the chat actually.
Yeah. Can you tell me what's the difference between like scikit and PyTorch?
Yeah, I'm just looking at it.
Basically in scikit-learn, because of like linear regression is much simpler, you can code it in a couple lines in scikit-learn. It basically just gives you a linear regression model.
Oh, okay.
It's kind of built for neural networks, which are a little bit different, which are, well, they're kind of what I described, right?
Right.
Two.
I guess what I'm trying to ask is why wouldn't you use PyTorch for the linear regression model, if that makes sense?
Oh, well, a linear regression model is very simple. It's just takes in the inputs and it multiplies it with the outputs. A neural network is like what ChatGPT is. It's what like it's much more advanced. It's able to make much more advanced like correlations.
What if you just like feed in a regular image of
Right, I understand.